In the beginning of the chapter, we alluded to the fact that the motion of electrons is what gives us a magnetic field, and that the motion of the electrons within a permanent magnet, such as an object that is magnetic, so what you would call a magnet that you put on your fridge, has something to do with the motions of the electrons inside of it. And so that is true. And so the simplest magnetic field that we can create is with a wire, because a wire has a current running through it. It has electrons in motion. So here we say that the strength of the magnetic field, so this would be in units of Teslas, is dependent on I, so the amount of current going through. In this case, the current is going down, and the distance we are from that wire. So as we go farther out, the magnetic field is going to drop off, and so it's going to be proportional to the distance from the wire. And mu naught is called the permeability of free space, not to be confused with E naught is the permeability of free space, is our electric constant. Mu naught is our magnetic field constant that we're going to use for most things to do with magnetism. So that's mu naught, it's 4 pi times the current divided by 2 pi r, and we're going to figure out why this denominator looks like a circumference next time. So we want to know what the direction of the magnetic field is. And to do this, we're going to use our right hand again, where the fingers again represent our magnetic field, and the thumb will represent the direction of charge. I'm not going to talk about a force yet, because there's not a force when we're creating a magnetic field. There's nothing else charged moving around. So, but we're going to use our right hand again. So point your fingers, give them a little wiggle. That's our magnetic field. And then our current is going to be our finger. So this might help if you grab something pointy like a pen, or this kind of pen or a pencil, but get the pointy end pointing in the direction of the current, and then grab it with your hand and point your direction in the thumb the current is going. And then we're going to wrap our fingers around this, and that's going to be the direction of the magnetic field. That the magnetic field actually goes around, makes a circumference around our charges that are moving. So basically the fingers still represent the direction of the magnetic field, so the magnetic field goes around, as shown in this picture, that the magnetic field wraps around the wire. So the magnetic field goes around this way. So this we would say is in a counterclockwise direction if the current is going off towards the right. Okay, so now we're going to look at this particular situation where I have a long straight wire and an electron that is approaching that wire. So what is going to happen to that electron? Is it going to be attracted to the wire, deflected by the wire? What's going to happen? First, we got to figure out what the magnetic field is due to that wire. So I'm going to point my pencil in the direction of that current. So it's going in the same direction. And then I'm going to wrap my fingers around it. And so on the top part of the wire, my fingers are coming out towards me. So there we would say that I'm going to write dots here, indicating that the magnetic field is out of the page. Then if I continue to wrap my fingers around, right, my thumb pointing in the direction of the current, then my fingers go back in down here. So this is, I'm looking at the tails of the arrow. So the arrows are going into the page, and here they're coming out of the page. So we have X's here, meaning into the page. And then so we know it's going into the page. And so the velocity and the magnetic field vectors are perpendicular to each other. So that's going to be the sine of theta, sine of 90. So it's just going to be 1. We do our calculations. So to figure out the force on the electron, the first thing we need to do is figure out what the magnetic field is. So we're going to use V is equal to mu naught I over 2 pi r. And it said we're 0.5 centimeters away. So this distance is 0.05 meters, and that is r. So mu is again 4 pi times 10 to the negative 7th Tesla. The current is given right here at 50 amps. And then we divide by 2 pi times 0.05 meters, and that looks like a value and that happens to be a tiny number, 0.0002 Tesla. And so then to calculate the force, we use the force calculation that we did last time. A force is equal to QVB, and so Q is just one electron, so 1.6 times 10 to the negative 19th coulombs times the velocity is given in the problem, 1 times 10 to the 7th meters per second times that 0.0002 Tesla, and that gives us a total force of 3.2 times 10 to the negative 16th newtons. So that's a tiny force, but it's on a teeny tiny little electron, so it's going to get it to move. And here are those values nicely written out, so we can either do it this way, or we can substitute in the B into the equation and go from there. So we get the same answer either way. Now we're going to use our right-hand rule again to figure out what direction. So take a minute, and this is what the lesson asks you to do, is figure out what direction the electron's going to go. But you're going to need your right hand again to figure that out. Okay, hopefully you've taken a few minutes to figure that out. But again, we're going to use our right-hand rule. We figured out that below the wire, the magnetic field is going in. So we're going to point our hands in. The direction of the electron is up, so we're going to point the hand up. And so the right hand tells us what a positive charge will do. So I have down here this kind of blown up region that's down here. And so the positive charge will have a force to the left. Now the electron, you can either use your left hand and do the same thing, or just say the electron's just a little nutty and is going to move to the right. The electron does exactly the opposite thing, and the force is in the opposite direction as the positive charge. So the electron is going to move to the right, and that means its trajectory straight up, but it's going to have a velocity vector to the right, and anytime we have a acceleration or force vector perpendicular to a velocity vector, we're going to get a motion that's curved. So it's going to be deflected by the wire and never quite get to it because of that motion of the magnetic field. And so eventually it's probably going to just sit here and go in a circle, but it's going to be a little bit more complicated than that because the strength of the magnetic field is changing. It's going to get stronger as we get closer to the wire. So the trajectory is going to be a little bit more complicated than that because of the changing strength of the magnetic field. And here are those trajectories again. The positive charge is going to be deflected to the left, and the negative charge is going to be deflected to the right. So this is one experiment we can use to tell what sign a charge is.